Welcome everyone to the second tutorial on advanced traditional controls. In this tutorial, we will be seeing the way with which we can design controllers for time delayed system. The time delayed system are the systems where the response to an input change is delayed. So, the main cause of delay in the system is transportation delay, and there might be inherent process delays like when we have huge distillation columns, the effect of any change in the feed will take long time to reflect in the product. So, such inherent process dynamics also lead to delayed processes. General structure of the delayed system is as given in here. So, the e power minus tau ds denotes the time delay of the system. The numerator by denominator is regular process model, which is g of s. The controller can be designed in two different ways. One is approximating e power minus tau ds and direct synthesis, and the other way is to use Smith predictor method. We will look at both these methods, and we will take an example and describe each method and then see the results. So, approximating e power minus tau ds can be done using two different ways. One is directly to use the Taylor series expansion, and the other is to use Pardes approximation. The main difference is that when we use Taylor series expansion, we will expand e power minus tau ds as 1 minus tau d times s plus tau d square by 2 factorial into s square plus etc. But in this using this expansion leads to additional zeros and the poles are left as such. When we use Pardes approximation, we can approximate both poles and orders poles and zeros in the same order. So, the first order approximation and second order approximation can be used for both pole and zero. So, this is the first order expansion of e power minus tau ds. The key point to notice, the e power minus tau ds has been split into two different parts, one containing e power the numerator containing e power minus tau ds by 2 and the denominator containing e power plus tau ds by 2. When we divide both of them, they will multiply and then add together to give e power minus tau ds. The other method of designing the controller is Smith predictor formulation. Now, let us take this system where Gm is the model of the system with time delay of 2 seconds. So, and then we define a desired transfer function. We use the same technique which we have already used in inverse response system, where if the system has any terms which contribute to unstable controller or instability in the closed loop system, we will take the desired closed loop function such that the term which results in this instability gets cancelled. So, we take the same e power minus 2s here also, and then define the g desired function. Using this, we use the same direct synthesis equation, which is C equals to g desired by 1 minus g desired times 1 by Gm. Now, we substitute everything and then expand it, but the key point to remember is that the e power minus 2s will get cancelled in the from the numerator of g desired and the denominator of 1 by Gm, but there is a e power minus 2s in the denominator which is in addition to that the one term. Because of that we will have something like 2s plus 1 into 3s plus 1 minus e power minus 2s, right. So, into s plus 1 into 2s plus 1 into 3s plus 1 divided by e power minus 2s. Now, these two will get cancelled, there is still some e power minus 2s left over here. So, that will approximate as first order Pade approximation and then do the computation. So, e power minus 2s is 1 minus s divided by 1 plus s. So, if we use that information and then do the design completely, we will end up with this controller formulation. Now, the main point to remember is that this controller will work and the closed loop control closed loop transfer function will result in this. This dictates the performance of the controller. So, when we look at this G desired, we have e power minus 2s divided by 6s square plus 5s plus 1. So, now this 6 is the time constant of the process, square of the time constant of the process. So, if tau square equals to 6, tau will be like 3 root 6. Now, this is some value which is close to 2. So, we will still get a process which is a little bit slower than the optimal optimal configuration. That is because of the way how we have chosen G desired. One of the ways to choose G desired is to have tau or the time constant which is very small. Here it is considerably large. Okay. Let's look at the Simulink example first and then see how the performance is. I have already configured all the parameters in this loop. As you can see, I have given a step input to the set point and I have configured the filter as given in here, and I have taken a PID controller block and I have given the parameters which are as calculated in this example. So, k is 5, tau I is 5 and tau d is 6 by 5. So, here the integral parameter is given as 1 by tau I. So, because of that I have given as 1 by 5, k is 5 and d is 6 by 5. Now, notice that P is not multiplying every element in this PID. So, because of that there is no need for this 1 by 5 here. So, we will take P to be 5, I to be 1 and D to be 6. If we this is where the total number of simulation time is given. Now, it is going to run for 100 seconds. This is the system transfer function which I have defined as such. So, I have multiplied all the denominator elements and taken the coefficients of s square, s cube, s square, s and 0. So, correspondingly I have given the coefficients. The way with which we can simulate time delay in Simulink is using the delay block in the library browser. I will just show how you can search for each blocks. So, you can just type delay, and here you can see all blocks which are available which contain the term delay. So, the main thing which we are interested in is either this transport delay or this delay. This delay uses this delay is used in discrete time domain. Since we are working in continuous domain, so we will use this transportation delay. Now, this defines how the time delay constant, and we have e power minus 2s there. Because of that, I have given 2 as time delay. Let us run this and then see how the output works. We can see the output as a graph from this scope if you double click it. So, as you can see, there is initially some time delay, but the process was able to reach the steady state. Now, if there are there is no control, how will the open loop transfer function look like? So, that we can check by changing the connections here. Now, notice that I have actually directly connected the step input to the system. So, essentially we are stepping the input, not the set point in this simulation. Let us run the simulation and see how the output works. So, this is the output response. So, as you can see, there is a considerable delay initially, and we can see that the process is taking at least like 12 seconds to reach the tau, which is the time constant of the process. If we were to now, the next question we can ask is that if the model time delay which we have and the process time delay are not matching, then how will this controller work for the processes which have different time delays. So, the key thing to remember is that we have seen this already in inverse response systems. If the process time delay and the time delay used for designing the controller are different, then there won't be there will be a deletion of terms in the denominator of the closed loop control closed loop transfer function. Because of that, there might be some RHP poles appearing in the denominator. So, we have to analyze how far we can tolerate the error from between the model and the process. So, we can now remember the controller design is for the process with 2 seconds time delay. Let us change this to 10 seconds and see how the process the control works. The controller will still work, but the process will start reaching instability. So, as you can see, the process starts oscillating here. So, any more model mismatch which is greater than 10 seconds will result in unstable control. So, as you can see, we can tolerate up to 500% error. Now, let us simulate for some 6 seconds time delay and see the output. So, it is way better than when it is 10 seconds, and let us look at 11 also, so that we convince ourselves that after 10 the process starts to become unstable. Now you can see that there is a oscillation which is in increasing magnitude. So this is diverging, because of that the process is unstable now. The other thing is, the PID controller which we have designed here is still not the optimal PID controller. If we were to use some a different PID controller which is with a different desired closed loop transfer function, we can actually improve the performance. That we can see from this simulation. So here you can see the process reaches the set point faster than this. So we can actually see multiple let's go back to the same configuration so that we can compare the outputs. We can compare two different signals using a single graph. So that will help us compare both parameters in a single graph, and we can see how both of them look like. So let's run this simulation. So the y-act is the controller without optimization. So y which we see here is optimized. So as you can see, there is a little mismatch here. So there is some offset here which is eliminated in the optimal controller design. Now let's go to the next topic, which is Smith predictor method. So in this method, we use a particular G desired and particular controller configuration, and compute the input by rearranging the closed loop transfer function. So we have if we assume the model of the function is k into, that is first order with time delay tau d, and G desired is also first order with time delay tau d, then US can be computed as this following equation. So what we can do is, we can actually configure each elements in the Simulink and then see how the closed loop performance looks like. We can also use the another interpretation which you have already seen in the videos, like this, where we have an error signal passing through the controller and a delayed version of input signal passing through another filter. Now this also can be configured in as such in Simulink, and we can compute the input values and then see the closed loop response. So the first way in which we can see, in which we have that U of s equals to now this method is what I have used in the Simulink tutorial. Remember this equation. So we have tau s plus 1 divided by k tau s plus k tau c s times E of s minus g star m of s into U of s plus gm of s into U of s. Now gm of s is the model transfer function, and gm star of s is the transfer function without delay. So here you can see the original system transfer function is 3s cube plus 10s square plus 6s plus 1. I have assumed the model to be 1 by 3s plus 1, and the delays I have configured as 2 seconds here and 2 seconds here also. So there is one term without delay which is getting subtracted here, as we can see here also. So, there is a subtraction and transfer function without delay times u of s. So, that has been configured here, and similarly the same transfer function with time delay, and then that has been added, and we do we check we give a step input to the set point and pass through the PID controller. The PID controller parameters I have chosen based on the previous analysis. Now, we can just run it and then see the output. So, as you can see, it is able to control the system even when the model of the system is taken as 1 by 3s plus 1. So, with Smith predictor method, even if the model mismatch is higher, we can still control the system. The other method where we have this error signal passing through one transfer function and the delayed input system passing through another transfer function. So, this can be configured in the Simulink as such, and that you can try the same for this system by yourself. With this, I conclude the time delay system tutorial. We will see on how to design controllers for uncontrollable systems and other advanced topics in the next tutorial. Thank you.